So you should have seen an Usain Bolt GC file, which if you open it up, should look kind of like this. I don't know what phrase, what state of expanded or unexpanded there is. But on Thursday last week in class, we watched a video of him running, which was kind of fun. And I showed you the graph of this for his 9.58 second world record run. So here's a file for you to play around with, and there are several tasks to complete. So task 1, here's the function. I want to display the graph of that function. So this is a, do you remember how to make the GC graph sort of question. But just between 0 and 9.58 seconds, I have it right now. I think yours would look similar if you see this little dot at the bottom. I have the graphing area minimized just so you can see all the text that's coming up. But there's going to be several things to do on this, and then we're going to do some other work together that involves the PDF/worksheet I'm going to pass out to you. But look at the graph for 0 to 9.58 seconds, make it show up, and then zoom in appropriately. This center section here, where there's the C that doesn't show up right now, it's blanked out, and dx and an m, that's some computations that's going to show, and we'll show the C in just a minute. But you don't have to mess with any of this for right now. Just complete task 2, which is plot points for the current value of time at x equals c, so that second, and then for the value of time dx later. So if you can open this up, think about it for a second, what is it that you need to tell GC in this blue area here to get it to graph that function that's previously been defined? Because if you look right now, there's nothing in the graph. Well, there might be something, but it's not what we're supposed to be looking at. There's some like built-in stuff all the way down at the bottom. But if I want it to graph that, what do I need to type here? Yeah. Yes, y equals f of x. So you have to use y's and x's and refer to this function f. You could alternatively type y equals and then write the whole thing out, but replace each of the t's with an x, but that's a lot of extra typing. So function notation is nice. You can define it once and refer to it over and over again, whether it's to get this to graph or to do other function evaluations, to plot some points, etc. How do I get it to do just 0 through 9.58? Just kind of like at the end of our quiz, right? So I'm going to put, on GC it's a comma, and then type the interval with, it doesn't matter if you have or equal to or not, just open or closed interval, 0 through 9.58. So let's see if I can remember what, yeah. It's a control shift to get the or equal to if you really want to. You do have to use x, not t. You don't have to use the or equal to's. It's indistinguishable in the graph. But if you hit enter, you should see the graph down below. And don't worry about zooming out to see the whole thing, because we're going to be looking at some stuff right around 3. In fact, you might see little purple blobs showing up there right around 3 on the graph. So we're going to zoom in on that. But, all right, we have a graph here. So our current value is C. What I'm going to do, if you remember, this had a little blacked out bar. I'm going to unblack this out if I can. Why isn't it letting me? There we go. If yours does what mine did, if you're unable to get to the little squares, just make a new command line, and then you can delete it later if you don't like having it there. But doing that sometimes kind of wakes up the program if it's frozen. Sometimes it does weird things. But if I want to show this, I'll make it as a red dot. So C equals 3, or I'm just turning it red for right now. Now, in the graph, you're not going to necessarily see anything because it's very small. But it doesn't really matter. We're going to use this value of 3 for right now that corresponds to where you can see a little something. There's some extra programming in this sheet that you don't have to fuss with. It's down at the very bottom. But that's why there's some weird purple things right around, well, it's 3 right now when C is 3. So it says no equation to graph for M. You don't have to put anything there. We're going to actually write something for it to compute below. But right now we're using x equals c as a current value of x, and it's 3. And I want to plot 2 points. One at x equals 3, but without using 3, I'll just call it c, so that I can change it later without having to go back into these coordinate points here. And then I want the corresponding y value, which, exactly like on the quiz, is f of c, right? And if you look at the graph now, you can see a black dot there. So go ahead and see if you can figure out what you need to state as the x and y coordinates expressions, so that you can have a second point that's dx later. So this is a time 3 seconds into the race right now, and we want one dx later. If you saw, there was something that said dx up earlier, but just if I want another point that's dx later in time, think about what I'd need in my x and y positions here. What would I put for x to make a second point that's dx later than x equals c? C plus dx. All right. So it's like 3 plus a little bit is what's going to show up on here. But to be more general about it, if I put c plus dx, and notice when you type in dx was already defined up above. GC knows what it is, not because it does in general, but because it says dx up here and it explains what it is. So what about the y value that goes with that? If it's supposed to be another point on this blue curve? Yeah, f of, right, f of c plus dx. So if you look at the graph, you're probably not going to see too much space between those dots. And here's why. Look back up at this. It says dx is 0.09 on mine. It can be as far as 0.1, or it can be smaller. And you can see if you slide this around, we talked about one time that there's an n slider that's built in. If you type n, it automatically creates a little slider down in this bottom gray area where you can play around with it there. But you can create multiple sliders. You can have multiple variables that you can play around with by physically dragging something back and forth. And the definition for this is I have, this is like an interval 0 to 0.1, where I go there in 100 steps. So I could have dx as small as 0, in which case that would be a single point. I can have it as large as 0.1, and I can have it that 0.1 is divided into 100 pieces. So that's a tenth divided into 100 pieces makes thousandths. So if I were really good at kind of jostling this, I could do this 1,000th at a time. Now, it doesn't look a whole lot different on this scale when we're zoomed out very far. But what we're going to do, remember, this is a graph of Usain Bolt running. This is his distance from the starting line as time goes on. So we're focusing in on what's going on around 3 seconds. Because right around here, from this level of zooming, it looks pretty close to line-like. You know, like a single angle. It doesn't look very curvy right where those black dots are. It looks fairly flat, not horizontal, but it doesn't seem to be curling right there. So I know it's a polynomial, but those 2 points especially, those are pretty close. So if I were to calculate the average rate of change between those two, the slope between those 2 points as if it was a straight line, the average rate of change, that slope, would be his average speed. So this would be y's over x's. Meters over seconds would be our units for a slope or rate of change computation between these points. And if it looks fairly straight, and we'll zoom in to take a look at this more carefully, but if it looks fairly straight to the naked eye, or if we play around with dx and see that it doesn't matter if dx is closer to 0.1 or closer to 0.05 or something, then we can test this out. So what we're going to do, see this m here is going to tell us what the slope between our 2 endpoints is. All we have to do is write a formula for m. So I don't want y2 minus y1 over x2 minus x1 precisely, those symbols, but that's what we need in our formula, right? we need y final minus y initial between these 2 points, right? So that we can use this in general, so we can change our location C, that parameter we defined, to be 3 for right now, and we can change it to be something else later and look at different spots in the graph. So what we're going to do is investigate his speed, looking at just small intervals at a time, and seeing if changing the size of the interval, the dx that we're using, has too much effect on what we get as that average rate of change. So it's not actually a straight line. I expect it to have some effect, but if it's down in the like hundredths or thousandths place of meters per second, maybe we can say, well, it's essentially the same speed. So go ahead and see if you can type in a formula for how to calculate that average rate of change of his distance with respect to time, using those 2 general points there with parameter C and interval length dx. So the 2 points to this are, first, do you know how to calculate slope or average rate of change? Second, do you know how to get GC to do fractions and stuff? So some of it's a physical task and some of it's a math task. But I think you've had more practice at this than back a couple weeks ago. So maybe this is easy by now. So rate of change. So I want my y coordinates in the numerator. Oops. Only C and X are next to one another on the keyboard. And then I want all of that divided by change in X. So there's 2 ways to do that. A, you can put parentheses around it before you start typing it, or afterward. Also, if you highlight all of this and then hit the divide key, the slash, it will put all of it in the numerator. So there's a couple different ways you can do that, with or without using parentheses. But yeah, notice when you subtract the x coordinates, you get dx, which should make sense. It's supposed to be change in y over change in x. dx is literally change in x. I can't just type dy because, well, that's not defined, but dx is. So dx, I've written before, that's the distance between those 2 points, c plus dx minus c. You could write that and it would come out to be the same. And what I mean by it comes out to be the same, if you scroll back up, you'll see now we have a value for m that appears. So m isn't something that's graphed, so the fact that it's yellow, you're not going to see anything yellow. But 10.828 is what is computed based on this function that models his distance from the starting line, looking at a specific moment around time 3, and specifically the moment I've got mine set to is using 1/10 of a second. So if I look from time 3 to time 3.1, in other words, that's the average rate of change over that 1/10 of a second, 10.828. So if I make that moment a little bit smaller, it would tell me more about his speed closer to time 3, but it also wouldn't apply for as long. So there's pluses and minuses to smaller intervals. If you use a dx that's extremely small, maybe it's more accurate, but it's more accurate at just a time that only is within that small interval. Whereas I can say this speed, remember an average rate of change or an average speed, this is the equivalent, the constant speed that would accomplish the same as whatever actually happened over the interval. So if you were actually running at a constant speed of 10.828 meters per second for 1/10 of a second, starting at time 3, he would have traveled just as far as if he followed that f of x function and compared the values f of 3.1 and f of 3. that change in distance would be equivalent to traveling at this constant speed for a tenth of a second, which would mean he went 1.0828 meters, because 10.828 for a tenth of a second, 10.828 meters per second for a tenth of a second, mdx tells you his distance traveled. Now, I want to take a look at this graph, and I'm going to zoom in a little bit around this area so we can see what's going on. So I'm going to do a shift-click sort of zoom, so hit the shift key and then drag a little box around this. So I'm not able to see quite as much of the graph anymore. I'm going to hide some of this. I did a lot of my text work. But you can see what that little purple blurb was. That's an arrow. And it's an arrow that goes from, at this point in time, 3 to 3.1. So that's our time, 3 seconds to that 3 plus dx, 3.1 right now, time. And so in this graph, I've got my dx here, and this is, right now, it's 0.1 second. dy I can see by looking here, and this dy would be mdx, which would be 10.828 times 0.1, so 1.0828. Easy enough to multiply by 0.1. That would be meters. So this is saying in this tenth of a second, he went just over 1 meter, which if you think about that, that's incredibly fast. But in any case, 10.828 meters per second is the speed here. Now, that's over this interval. Because there we go. With dx equal to 0.1, we get m as, I'm just going to write this down because I'm going to change it, 10.828. Now, if I go and change this to something else, you can see that m varies. It's not too much different. You see, like, it's when I make this 0.001, that's the smallest number on here that I can actually get a result for. If I change it to 0, notice I get no result for m. You can't have a rate of change if nothing has changed. So I have to change a little bit, and the increments on this slide are built to be 1/1000th at the smallest. So at the smallest, you can see those two dots look like they're right on top of one another again, just like they did when we were zoomed all the way out and saw it when it was 0.1. So these are really, really close together, and I could zoom in and see what all is going on here. But I notice this rate is a little bit smaller. That should maybe make sense if you remember the overall shape of the graph. You started out from a stop and sped up and was speeding up for a while until, if you look at the whole graph, it was maybe around like 6 or 7 seconds where it looked like he was kind of going the same rate for a while, a while that you could see when you're looking at 10 seconds at a time. Now, when I'm looking at a tenth of a second here, and 1,000th of a second is this tiny part, maybe that's closer to a constant rate, but it only applies for right here. It only applies right around 3 to 3.001 seconds. So for 1,000th of a second, he was going at this rate, which is slightly smaller than this by, what is that, 1/20th of a second or something? Or 1/20th of a meter per second, I should say. But as I use values that are larger for dx, I get slightly larger rates of change. And that should make sense if we realize this was from a distance. We could kind of see it was curving up from the beginning, and this is where it first started to maybe look flatter. So it's still curving up a little bit. And this is a polynomial, so we know it's actually curving everywhere. But it's not curving too much. The difference between 10.81, 10.82, 10.83 meters per second is not extremely much. However, that is probably the amount of difference that it took for him to beat his competitor. This is a world-class athlete sort of race. But for rounding purposes, we wouldn't want to say, oh, they're all running about the same speed and leave it as that, because yeah, you're running about the same speed, but somebody won. So we could be more precise by talking about speeds over smaller intervals. Just pick anything smaller. But again, when you gain precision in what that rate is, it applies to a smaller interval of time. So you gain one thing, you lose another. It's kind of up to you what is more important to you. So I know this is it's an exact average rate of change. If I were to graph a line that goes through this point with a slope of 10.828, I would see that it'd probably be pretty darn close to being right on top of this blue polynomial function. But I know that the polynomial function gets steeper out here, so at the beginning it's flatter in order for this to be an average. So the line would probably be a little tiny bit above the blue curve at the beginning and end up just finally meeting it here. So it's curved upward, straight line connecting the endpoints, but very small amount of space in between. So what I've got for you as a task is to investigate the values at different points during his run. And the purpose of this is for practice at understanding how changing rates of change can be seen to be nearly constant over small intervals. And playing around with GC to be comfortable with zooming in and out on a graph and looking at how to see rate of change. So I'm going to pass these down and explain this clearly in a minute. But what you see is a kind of a table of values to fill in. And I'm going to assign tasks to you by rows because it's kind of repetitive. I want you to do some of it, but you don't need to do this 30 times. We'll go 10 minutes. So what we just did is calculate the value of m when c is 0.3 and dx had a variety of values. So that's symbols and numbers wise. What we just did concept wise is we were calculating or having our GC calculate speed around time 3 over different small intervals. An interval anywhere from 1,000th of a second to 1/10 of a second, and looking at those rates of change in meters per second. So in terms of what we're doing here, so we just did 3 seconds together with dx equals 0.1. We had 10.828. Now, I believe this actually says round to, does it say where to round? Let's round to 3 decimal places, as long as I did it on that one. On the GC file, I would suggest do zoom in and out. You don't actually have to do any zooming in order for it to show up. You can still see the results without zooming in. Like you could have it just left here and do some computations. Oops, where's my, sorry, I'm drawing here and I'm not trying to. No, that'll do it. So if I go down to 0.01, try your best. You can see, oh, 10.7825, so a little bit less. Or if we go to 0.001, which is the smallest you can get, 10.778 to 3 decimal places. You can, wherever it's convenient to round. If it's a weird number, like just round off where it's convenient, but 2 or 3 decimal places. But what you're going to be doing then is, for instance, that first row. Instead of looking at time 3 seconds into the race, let's look at 1/4 of a second into the race. Now, graph-wise, we're not there right now. So I'm going to zoom back out so I can see what on earth it is we're doing. This was zoomed into being around time 3. So with those dots there, you can kind of pick out where it is when you zoom back out again. But if I want to see what's going on around time 1/4 of a second into the race, and you see this looks much more horizontal in nature, so it's harder to see that there's vertical change, i.e. distance being acquired, but that should make sense. It's the first 1/4 of a second into the race. He's not going very fast yet, even though he's a very fast person. But you can see that with 1,000th of a second as the dx as our interval width that we're thinking about, thinking of just a small moment here, letting going forward in time by just a 1/4,000th of a second. When we're at a 1/4 second into the race, we've got a speed of about 2.1, 2.11, how many where you want to round this off, meters per second. We know it was 10 point something by 3 seconds into the race, so clearly the graph is curving, as in he's speeding up. His rate of change, or the steepness between points, is getting steeper and steeper. But we should be able to measure that and give it a number, not just say it's steeper. So here's how we can give it a number. So here's what I would like to do in terms of this sheet and divvying up tasks so we can compare numbers in just a moment. So let's say that, let's see, how many rows we have? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. All right, so if you're in row 1, and if this is working it, if you're in row 1, do 0.25 seconds. Actually, row 1 and 2, do 0.25 seconds. I'm going to have everybody do 2. If you're in the second row, or third row, sorry, rows 3 and 4. Hi, right, there we go. Do half a second, rows 5 and 6, 7 and 8, which would include you guys back there at those two tables. That's 1, 2, 3, 4, 5, 6. Oh, you're 7, sorry. Okay, so 7 and 8 over here is on the other side of the walkway, and you're 7. All right, and then start over again. So if you're in row 1 or 2, you're going to do 2.0 seconds. We already did this one, so nobody's doing that one. If you're in row 3 and 4, you're also assigned 5 seconds. 5 and 6 are also assigned 7 seconds. And then 7 and 8 also get to do 9 seconds, which is kind of an interesting one. So take a few minutes, see if you can get these computations at 3 different dx sizes, because not only are we going to look at what the values are, we're going to look at what the pattern of the values are. Right. So, oh, changes between 10. Okay. Sorry about that. All right, so a couple of issues I wanted to mention that some of you have been having with just GC stuff. Remember that parentheses can be used for two different things. One for multiplication, two for function notation. And depending on exactly the build and model of your computer and keyboard and whatever, sometimes it kind of knows what you mean and sometimes it does not. You can always make sure that it knows that you mean function notation parentheses as opposed to multiplication by hitting Control 9 as opposed to just the Shift key and the 9 where the parentheses are. If any of you have foreign layout keyboards where the parentheses aren't above the 9, it's wherever the parentheses are. So let me clear this off for a second because I have answers someplace else. All right, did I open it recently? Nope, I'll open it the hard way. Hold on a second. Got a lot of stuff in here. And Usain Bolt. Where are you? Oh, not in quizzes. Sorry, lots of stuff on here. So I have this rounded to 2 decimal places. Take a look at what you've got for your rows. I'm going to put this back up in a minute, but I do want to show something GC function notation wise. We'll go back to this in a second. If you got numbers that seem to be the same sorts as what are up here, then you're good. If you're getting numbers that were completely out of whack, like 500 or -87 or something like that, there are 2 places, again, where I saw most of the errors in this. And this was in function notation and in some cases just variables. So if you see font suddenly look different, like spacing looks different or italicization looks different from how it did in a previous line, and you're having issues, that's probably one has to do with the other. So in this, if you have something that, so f of c here, see how the f and the c and the parentheses are all squished right together, there's no space in there? If you see something that looks more like, and I'm going to have to type times because mine won't let me. If I type multiplication in there, it still looks like f of c, but now if I go to look at my computations, they're all going to be wrong. If you can see the difference between the spacing for when it is actually multiplication using parentheses and when it's function notation, if you see extra space and you're supposed to be using functions, that means that GC didn't interpret what you wrote as function notation. So how you get that to not happen is, first of all, if you start typing and you hit parentheses and you see a little time sign pop up, it's going to do multiplication. So watch as you're typing. But if you hit Control 9, you'll see parentheses that are right next to the F. There's no space between it. It's a nice italicized F. It leans over into the parentheses so that it understands this. Also, if you copy and paste, most of the time, if you copy and paste from text into functions, it doesn't do it. Every once in a while, it will. But I had a couple of you with issues where your dx was all italicized, so it was taking it as a letter D and a letter X that were multiplied together. But if you notice, this dx up here is not italicized. To define strings, whole phrases if you want, or whole words if you want to be variables, there's a certain technique to do that in GC, and you shouldn't have had to do it because it was done already in the sheet that I gave you, but it's like hit a slash and then dx, and it'll lump those all together as a variable name. That way you don't have to have single letters be variables. You can define whatever you want. But in any case, if you look at these and if you have extra spaces anywhere between the F's and the parentheses afterwards where that's supposed to be function notation and you're getting errors, that's why. It's not understanding that you meant function notation. Hit Control 9 to get the parentheses that indicate input is coming next. So in any case, on these, other thing, and I will look up exactly what the keystrokes are. I know that just physically sliding is kind of cool to watch, like the smaller, larger effect from a distance when you're zoomed out. I'm going to zoom out to someplace else. Oops, not 0.77. where's the end of this? There we go. Shift click. So it's nice to, you can zoom in and see, like, oh, it's sliding. And so you can see like larger, smaller, and compare the dx values and the dy values and see that it makes a difference where you're at. So it's kind of cool for that aspect, but it's kind of hard to stop exactly where you want. And so there is a technique with keyboards to be able to nudge it to the next incremental size, and I forget what it is. It's something like Control Command arrow key or Control Alt arrow key or something to that effect. I will look it up. It should be someplace in your documentation how to get it to go to the next one if it won't automatically. But for our purposes today, this is just an estimate. So it's okay if it wasn't exact. If you're off by 1,000th of a second in your dx, probably your 4th and 5th decimal places for your speed, your M computation will be different, but not prior to that. So in any case, in terms of this, let me pull back up these values that I had. So if you're in the first or second rows with this dx of 0.1, 0.01, 0.001, you can see as x is, when x is right near the start of the race, when we're at a quarter of a second, half a second, 1 second into the race, in general, regardless of what size of dx we use, we have smaller speeds, right? So at the beginning of the race, he was going 2-something meters per second, then 3, 6, 9, 7, 10, 11, 12, 11. Started slowing down. That's the, I already got this covered, I'm winning. I'm gonna just take one last step here. So you can see it faster, 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 and based on these, now these are several, this is like a whole second apart, but around like 5, 6, 7 seconds, the speeds all look the same for a while. So I'd be curious to know if you picked like a time like 5 seconds and took dx to be 1 or 1.5, if it would be close to still that same like 11.9 meters per second, because it really looked, even from fairly close in, it looks very, very flat, but from a distance it looks very flat also, and we know it's all a curved polynomial graph. But thinking about what these dx's, the pattern of them as we go across, that's a whole other piece of information that it's telling us about the graphs and about his speed and his distance from the start. So we know from seeing the whole thing without knowing the rates that the graph was curved upward. At least at the beginning it was curved very much. So if I were to take a smallish interval between 0 and 0.25, I get the speed 2.4-ish meters per second. If I go a lot closer to 0.25, it changes significantly. It's 0.3 of a meter per second less by looking at a smaller amount of time, meaning over that interval, if I'm using an interval of 1/10 of a second, over that interval, he clearly was speeding up, even over that 1/10 of a second. Because if I look at the average rate over a 1/10 of a second, compare it with the average rate over the first 1,000th of a second, the first 100th of that 1/10 of a second, his speed was appreciably larger over the whole interval than over the much smaller interval. So you can see from the pattern of these, if I am looking at intervals that are closer to the beginning of the interval, so looking at these are very small, close to these times, if the numbers get larger as I go back across or take larger intervals, that indicates he's been speeding up. So he's been speeding up. These are all kind of the same, 10.78, 10.78, 10.83, right around 3 seconds into the race. Whether I look at 3 to 3.01 or 3 to 3.001, I get about the same average rate of change, the same speed for him, 10.78 to 2 decimal places. So his speed wasn't really picking up between 1,000th of a second and 100th of a second. Past that time 3 is about the same, at least to 2 decimal places. And same with 5 seconds and 7 seconds and almost with 9 seconds. But in the rest of these, time, a quarter second in up through this 7 seconds, all of those lines there, when I used the larger interval, I got a faster speed, indicating over that longer amount of time, he's going faster, 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 which you'd expect for somebody who's trying to run as fast as they can and are good at it. But this one, not true. At 9 seconds in, if I look from 9 to 9.001 seconds, I get an average rate of 11.7, almost 11.8 meters per second. If I look a little farther, I actually get a rate that's slightly less. If I go from 9 to 9.01 or 9 to 9.1, it's even less than that. So we can see by this point in time that it's no longer the case that as I pass 9 seconds, he's going faster and faster. As I passed 9 seconds, he was close to this speed right around the smallest interval I could measure, around 9 seconds. But if I look a little bit longer, his average speed was a little slower. He must be slowing down. Already at 9 seconds in, he finished the race in 9.58 seconds. So, the bottom part of this sheet, it's a little bit hard to do kind of freehand. So I just want to take a look at what this is. This is using the dx equals 0.001 and just plotting the data that we have. Now I named this as your book will, as we're going to talk about. This is our topic for post-quiz Thursday. R sub f of x, the rate of change of f of x. That's going to be the notation that we use for this. So we had rates at whatever it was, 9 different times during the race that we computed approximate rates by doing average rates of change over very small intervals. And at the beginning, the very first part of the race, he was running relatively slowly, fast if you ask me, but 2-ish meters per second, then 3, then 6, 7, 8, 9, 10, 11, almost 12, yeah, 12 and a half-ish, and then back down to 11. So you can see that he's slowing down, not only because this went from 11.9 to 12.5 to 11.6, but also that the farther you look out, the slower the speed you get is. So if we were to look at maybe something like 8 seconds or 8.5 seconds into the race, you might notice that the speeds are kind of equal all across the board, and that would indicate, oh, well, regardless of if I go out and right around here, these are all about the same, right around 7 seconds. Whether I go out 1/10 of a second or 100th of a second or 1,000th of a second, my rate of change all comes out about the same. That probably means it's about as fast as he got, because he'd been speeding up all along. And then we know he starts to slow down. Now, this is the sort of graph we're actually going to be focusing on for the next couple of weeks up through our test. So this week and next week, looking at graphs of rate of change and analyzing what happens if I know rate of change and I want to know what happens because of it. So just be prepared. We're going to be looking at graphs of things like this, not like his distance from the starting line that went from 0 to 100, but graphs like this where I see his rate of change. Notice the dependent quantity here is meters per second for units. So his meters per second, we calculated a few different values that vary from almost 0 to 12.5. And we didn't calculate values everywhere because that would take the rest of the year to do every 1,000th of a second throughout the whole race. But we can kind of guess that, well, in order for his speed to have gotten from 2 something to 3 something, it must have passed all the numbers in between, because he's not teleporting. He's actually speeding up to get from one place to another, and to have his speed increase, it must have passed all the numbers between the numbers that we computed. Like, you can't get from 2 meters per second to 3 meters per second without passing 1.5 meters, or without passing 2.5 meters per second. He has to have done it at some point in time, even though we didn't calculate that value. So just in terms of estimating, this would be a picture of, just kind of rough connect the dots style. Well, we started someplace, and I just estimated the beginning part here, and then connect the dots with the rest of these values at, so this point here is at 7, 12.49, supposedly. Now, the y-axis isn't isn't subdivided that precisely. So about 12 and a half is where this is. 7, 12 and a half. Meaning, at 7 seconds into the race, if I use a small interval around that, I can estimate his speed to have been about 12 and a half meters per second. Now, I can't say at that one point in time, because at any point in time, I can go that fast. He's not moving at all. So I have to have 2 points in time, but I can imagine them to be as close together as I want. For computation and GC purposes, I just pick 0.001, 1,000th of a second apart. But we could go back and change that. We could add in 0.0000001, and we could zoom in farther and make this a more precise estimate of his speed near a single point in time, but it has to be just near, because we have to have change in order to have rate of change. So, as I said, this notation, R sub f of x. We're going to be using this, we're going to name a lot of our functions R. So we're going to have subscripts to indicate the rate of change of what. So if I want to talk about the rate of change of the height of something, something's moving upward, and I want to talk about how fast it's moving upward. If the height's designated h, the rate of change of the height, or the speed at which it's going up, I can go R sub h. So we're just going to use this notation so that we can talk about it, remembering that it's rate of change, and indicating with a subscript what the original function was, like what it is that's changing at that rate. So in this case, we used f for its distance from the starting line. If you want to use d for distance, or s, or pick your favorite letter, you could do that. But this one was defined as f earlier, so that's why we have R sub f here. So, just as kind of a preview then of where we're going next, done with Usain Bolt for right now, but we will get back to him because he's the meaning of physics and math, I'm pretty sure. Let's see, oh, here we go. All right, so, yeah, we talked about this already, but we did enough with that. Pick up different. All right. Oops, I am not at the beginning. There we go. All right, so just recap, because we're going to use all the same terminology. All the same relationships are still important. It's just that we're going to start from knowing rates and calculate what happens because of them afterward. And we've done that a lot already. It's like, oh, we know that the flag is decreasing at a rate of 0.75 feet per minute, or whatever this was. We started using rates and seeing what happens because of them. So a moment, again, we talked about this already last time, but a moment, this is this kind of pick a small interval, and let's just look within this small interval. And small is vague, but if we pick something that's small enough so that it seems, or so that it calculates to be close enough to constant rate of change for our needs, then that's good. So this moment at x equals a, or a moment with x equals a moment around x equals a. Sometimes in advanced math textbooks, they'll call it a neighborhood about x equals a. It's the same terminology, it's used throughout. But this moment is a small interval of the independent variable that includes a. A could be at the beginning, the end, the middle, anywhere. I'm just using a as a generic x value. So we say the moment at a to talk about not just one point in time, but a small interval including that, wherever the a value might be within that interval. And the differential in x, which is our fancy words for this dx, or change in x, is just the variation that happens in x within that moment. So we usually think about dx, we can be anywhere from 0 to, well, however long the moment is that we've chosen. So maybe as x varies from 0 to 0.001 seconds, when we're looking at a moment, x equals 3 seconds into the race, we could describe the change in position for Usain Bolt racing, or we could describe his speed during that interval. But a rate of change at a moment exists if we can pick an interval small enough so that it seems like there's a constant rate of change relationship between changes in x and changes in y. So if you can imagine with the slider that we had, 0.001 was the smallest you could get besides 0. But if you change from 0.001 to 0.01, and the m computation comes out to be about the same or the same to 3 decimal places, which is good enough for your needs, then you can say, oh, in this moment, in this size of moment, I can see that there's essentially a constant rate of change. So I can use constant rate of change techniques to move from knowing a rate to knowing what happened due to it, or vice versa, knowing what happened to finding a rate. So visually speaking, if something's relatively smooth, doesn't have corners like an absolute value graph, or weird endpoints like a square root graph has an endpoint, or some other sorts of roots have weird curved cusps, as long as there's not bizarre points like that, you can zoom in far enough on anything smooth to find constant rates of change over at least microscopically small, infinitesimally small intervals. The size that you need to zoom into depends on the function itself. Now, we'll talk about some weird exceptions. If you look at the end of chapter 3, I think it is, some of those later sections talks about wrinkly functions for which there's no constant rate of change anywhere. We'll take a look at that. It's kind of interesting stuff, but we're not going to work with those because they're not very useful for purposes of studying rate of change. But here's where we're going to start Thursday after your quiz. Look at the graph on the left. The graph on the left is representing a rate of change of the amount of water in a tub, hold on, in gallons per minute. So that red graph on the left is a graph of a rate of change function. Now, it's not a very difficult looking function. It seems to have one value throughout, one constant rate throughout. The graph of constant rate of change, when you're looking at the actual rate graph, has to have one y value, one dependent value throughout. So in this case, it looks like 1.5 gallons per minute all the time. If you know that the tub is filling, it's positive, at a rate of 1.5 gallons per minute all the time, you can tell something about how much water there is, but you need to know one other piece of information. If I asked you, if I said, oh, the tub's filling with at a rate of 1.5 gallons per minute, how much water is in the tub now? Like, well, how long is now from when you started doing that? And was there anything in it when you started? Like, was it slower before? So you have to know more information besides just a rate. Like if I told you, I'm driving down the highway at 60 miles an hour, where am I after an hour? Well, you know I've gone 60 miles, but you don't know where I started. So knowing a rate isn't knowing everything, but you can recreate a lot of information from just rate of change. And if you have constant rate of change, at least for small intervals, and this is like 5 minutes, then you can say what happened during that small intervals. In 5 minutes at 1.5 gallons per minute, I'd have 7.5 extra gallons of water in the tub. Don't know if I started from 0 or something else, but during that change in time, I know my change in water. All right, to be continued Thursday, but we'll have a quiz at the start of class on constant rate of change.
So my quiz wasn't graded on campus, and I think it's because I was down
Have you had recitation yet?
since the quiz.
Yeah.
No.
Okay, so you'll get it back in recitation now, I'm sure. TA probably just did the Monday people first and the Wednesday people afterwards. You'll have it soon. Thank you.